Hi, I'm Zeev Scully, and today I'm going to tell you about how to schedule near optimally in multi-server systems. So this is joint work with my colleague Isaac Grosov and advisor Mor Harchelbalter. So today's talk is going to be about multi-server scheduling. But before we get to that, I'm going to tell you about some of the background in single server scheduling and what's been done in that space. And the specific single server scheduling model we're going to consider is the MG1 queue. So the MG1 is a classic single server queuing model. It's got one server, which can serve one job at a time, and a queue, which can hold any number of jobs waiting for service. So this is what a job looks like in this talk. It's going to be a test tube, whose height is its size. That's the amount of time we need to serve the job for it to finish. We're going to represent service as filling the job with water. And so the amount of water so far, that's the amount of time the job has been served so far. We're going to call that the job's age, and then the rest of the job is its remaining size. Now we have jobs randomly arriving over time, and the M and the G in MG1Q tell us what this random process looks like. There's a general size distribution S from which each job size is independently drawn. We've got Poisson arrivals at rate lambda, and this gives the system load rho equals lambda times EFS. And this is the fraction of time the server has to be busy to keep up with demand, which has to be less than 1 for the system to be stable. So that's the MG1 queue, and today we're going to talk about scheduling in this queue. So the scheduling policy decides at every moment in time which job to serve, and it does so preemptively. So we can decide to switch out the job in service for another one, and we're going to assume that there's no loss of work or preemption overhead in this talk. Now our scheduling objective is going to be to minimize response time. So a single job's response time is the time from when it first enters the system to when it leaves. And this includes both the time the job spends in service and also time the job spends waiting in the queue. And because the scheduling policy affects when jobs wait and when jobs are served, response time of jobs is greatly affected by the scheduling policy. Our goal in this talk is going to be to design a scheduling policy that minimizes mean response time. That is the average response time over all jobs. So let's start with a very simple version of this problem. Let's say we're in a single server queue, we've got these jobs in the system, and we know each job's size, age, and remaining size. How should we schedule to minimize mean response time? So it turns out that the right idea for minimizing average response time is to always try and kick jobs out of your system as soon as you can. And the policy that does this best is called SRPT. It stands for shortest remaining processing time. And what it does is it always serves the job of least remaining size. And so in this example, SRPT would serve this job over here. And it's not too hard to show that SRPT minimizes mean response time. So that's a really easy version of the problem because we know each job's exact size. What about the harder case where we don't know job sizes? Say we have unknown job sizes. We don't know the heights of any of the test tubes. How should we schedule now? And even more basic of a question, how do we even decide what jobs to schedule? What information do we have to use? So even though we don't know how long any job is going to take, we can still track how long we've served each job so far. That is, we still know every job's age. And even though we don't know any individual job size, it's still very reasonable to assume that we know the distribution of job sizes. That is, the overall size distribution S from which each job size is drawn. And this is a reasonable assumption because we might keep track of historical data and get, oh, this many jobs are small, this many jobs are big, this many jobs are in between. So our goal in unknown job size scheduling is to leverage these two pieces of information, the distribution and each job's age, to decide which job to serve. And this problem has been studied, and there's a policy proposed called the Gittins policy. And what the Gittins policy does is it kind of strategically uses each job's age and the size distribution S to decide on a rank or priority for each job. The rank is a number where lower is better. So this job might have rank 4, this one might have rank 3, this one might have rank 5. And Gittins always serves the job of least rank. And Gittins is so clever in how it assigns these ranks that it turns out that Gittins minimizes mean response time. It's a much more involved argument than the SRPT case with known sizes, but what this means is that in the case of unknown job sizes, this problem is solved in the single server. Gittins minimizes mean response time. So here's what we've talked about so far. we talked about minimizing mean response time in the MG1 queue. With known job sizes, the optimal policy is SRPT. With unknown job sizes, the optimal policy is Gittins. But these aren't the only scheduling problems one can imagine. You might imagine maybe we have an estimate of every job size, but that estimate is noisy. Or maybe jobs have multiple stages and we know which stage we're on, but we don't know how long each stage is going to be. So there's a wide variety of partial information scenarios. And you can imagine single server scheduling with partial job size information. And it turns out that Gittins policy is actually more general than just unknown sizes. It also solves these partial information settings. In fact, Gittins is less a single policy and more like a family of policies, a sort of general policy construction. And it covers not just unknown sizes, but this huge variety of partial information scenarios. In fact, Gittins even works with known job sizes, and SRPT can really be viewed as a special case of Gittins, in which a job's rank is just its remaining size. So least rank corresponds to least remaining size. So, to sum up, when you're scheduling in the MG1 and trying to minimize mean response time, the optimal policy is some flavor of Gittins. So, that's the background on single server scheduling. Let's now talk about the much harder problem of multi-server scheduling. And the multi-server model we're going to talk about is the MGK queue. So this is basically the same as the MG1 queue, but now instead of one server, we've got, you guessed it, K servers. And we're going to use the convention that each of these K servers has speed 1 over K. So it's like K small servers or K slow servers. And this means that the total service capacity of the MGK under this convention is always 1. And so compared to the MG1, we're going to use the same definition of size distribution, same definition of arrival rate, same definition of load. But now at the server, the job is going to go kind of K times slower. So the MGK you can kind of think of as really a restricted version of the MG1, right? Because now the scheduling policy can't use all of the service power on one job. It has to split it between K different jobs. And if there are fewer than K jobs, the scheduling policy has to leave some servers idle. So the MGK is kind of a more restricted setting than the MG1. But we can imagine kind of designing multi-server versions of SRPT and Gittins that might be good in the MGK. So for example, multi-server Gittins would serve the K jobs with the K lowest ranks instead of the single job of least rank. Similarly, multi-server SRPT would serve the K jobs of least remaining size. And so we might ask, is multi-server Gittins, is multi-server SRPT, are these good policies in the MGK? So let's talk about what's been done in the past to answer this question. So I've named this table originally optimal policies, but it turns out that when you talk about multi-server scheduling, optimal is kind of intractable. So we're going to relax and start talking about near optimal policies. And the prior work that's been done on near optimal mean response time in the MGK, the name of the game is generalized MG1 strategies. So for example, in 2018, in prior work, we actually took the MG1 analysis of SRPT and generalized it to the MGK to get a mean response time bound on multi-server SRPT. And this multi-server mean response time bound looks like this. It says that ETK, K-server mean response time for SRPT, is at most ET1, single server SRPT mean response time, plus K minus 1 times this slowly growing function of load. And it turns out that this slowly growing function of load is in general the smaller term. And so this basically means that K-server SRPT is near optimal in the MGK. And so that's a really nice result we have in the known job size world. But so a natural question is, can we do the same thing for partial information or for unknown sizes, right? Can we get an MGK response time bound for Gittins? And we've been trying to do this actually for basically since 2018 when we published the SRPT result. I've been bugging Isaac, hey, can we, this strategy we used for SRPT, can we use it for Gittins? And over again, we keep running into problems. And the kind of core problem is that the strategy we used for SRPT to translate the MG1 analysis to the MGK used worst case techniques. And these worst case techniques work really well when you've got known job sizes, because there's sort of no uncertainty. You have a sort of worst case bound on when a job is going to finish. But in the unknown or partial information setting, you don't have these sorts of worst case bounds. And so you can't really get good bounds on the MGK using worst case techniques on Gittins in these two more difficult settings. We actually published a paper in Performance last year that kind of takes a first step in this direction, but it is subject to all sorts of conditions on the job size distribution. It's basically not the right approach. So this is the state of the art. We don't know whether Gittins is a good idea in the MGK because the existing techniques for MGK analysis don't work for Gittins with unknown or partial information sizes. That brings us to this work. So our contributions in this paper are two. The first is we introduced new techniques for analyzing mean response time in the MGK. And we use these techniques to prove that Gittins has near optimal mean response time in the MGK. And so to put this in context with the prior work, here's the prior work. We knew that SRPT was good in multiple servers. We didn't know about Gittins in partial information and unknown size settings. This new result covers SRPT and Gittins in the known sizes, unknown sizes, in between partial information settings. And we get the same type of mean response time bound in all of them, bounding K-server mean response time as single server mean response time plus this slowly growing function of load. And you might recall that's the same kind of bound we got for SRPT before, but now it also covers Gittins in these more general settings. So that's our main result. Under Gittins, we have this mean response time bound in the MGK, which is the most general result of its type. And underlying this theorem is kind of one key concept, and that concept we call R-work. So in the rest of this talk, I'm going to tell you a bit about what R-work is and how it helps us prove this theorem. So let's start with what is R-work? And well, to start with that, we're going to go to what is work. So the work in a queuing system is the total remaining size of all jobs. And I should note that, as the scheduler, if we don't know job sizes, we might not know what the work in the system is, but there's still some random variable, which might not be known to the scheduler at every moment in time, which is the work remaining in the system. So that's what work is. And work goes up and down over time as jobs arrive and as we work on jobs. So our work is basically a subset of the work in the system. Specifically, it's the work that's relevant to a job of rank R. By relevant, I mean this is work that would be prioritized in front of a job of rank R. So it's work that happens on jobs while they have rank less than R. So to draw a picture of this, rather than looking at these test tubes, let's draw the rank of each of these jobs. And I'm going to draw a line, which is like a rank cutoff at some value of R. And what our work is saying is it's saying, let's put on some kind of rank R sunglasses that only show us jobs of rank R and below. And the work that those jobs will have while they're still below rank R, that's what our work is. And so here's how we analyze response time using our work. So remember that our goal is to get a mean response time bound on the MGK in terms of mean response time in the MG1. And what we're going to do is we're going to get this bound by going via our work. So specifically, there's a two-step process. The first step is in each of the MGK and MG1 to relate mean response time to mean R work. And then the second is to relate the mean R work between the multi-server and single server systems. So let's start with these vertical edges. So how do we go from mean response time in the MGK to mean response time, to mean R work in the MGK? So we introduce a new theorem that does exactly this. It's a new formula for mean response time, which says that mean response time is 1 over lambda times this integral of R work from 0 to infinity. And this theorem tells us how to translate between mean response time and mean R work. And it works in the MGK, and it also applies to the MG1, the exact same theorem. In fact, this theorem applies to pretty much any queuing system. So this new mean response time R work link covers the vertical edges. How about the horizontal edge? For that, we introduce a second new theorem, which is a work decomposition law. It basically says that R work in the K-server system is R work in a single server system plus a kind of complicated term that you can think of as the R work of at most k-1 jobs. And that complicated term, it's a little bit too difficult to describe in this talk. You can see the paper for details. But it turns out that that term is small enough that when we translate that R work difference back to a mean response time difference, we get the bound that we were looking for. So, to sum up, today we talked about how to minimize mean response time in the MGK without known job sizes. That is, unknown job sizes or partially known job sizes of some sort. And in the single server setting, we know that Gittins is the right policy. And so we were wondering, can we analyze Gittins in the MGK? The problem was that these prior MGK techniques really needed known job sizes or other kind of worst case information about the system that we didn't have in the unknown or partially known job size settings. So to get around that, we introduced a completely new way of analyzing mean response time. And it works in the MGK, it also works in the MG1, it also works in other queuing systems. And it's based on this key concept called R work. And using this new way of analyzing mean response time, we were able to show that Gittins had near optimal mean response time in the MGK. So that kind of concludes the main portion of my talk. I'm going to conclude with like a few comments about future work. So one reason I'm really excited about this paper is that the key steps, those two key theorems in the box, the vertical edges and the horizontal edge, neither of them is very specific to the systems we talked about in this paper. So for example, that vertical edge going from mean response time to mean R work, that holds in basically any queuing system. It holds in the MGK. It would also hold in immediate dispatch systems, where as soon as a job arrives, you have to choose which server it goes to, and each server has its own queue. And so we're really hopeful that we can use these same techniques to analyze a wide variety of multi-server systems, not just the MGK. So if you have a multi-server system that you're trying to analyze, or if you have any other comments or questions about this talk or this work, feel free to get in touch via email. I'd love to hear from you. Thanks again for your attention.